Improper integrals. Or otherwise known as misbehaving integrals. Not. Now, I like that misbehaving, but it's not. It has nothing to do with that. Actually, some of these integrals are very well behaving. So let's see what there are. There are two types. There are two types of improper integrals. And this will give you an idea what we are talking about. The first type will be, by the way, when we are talking about improper integrals, we're talking about definite integrals. Okay? So we're looking at case type 1 is the one that have infinite intervals, or infinity in their intervals. So infinite intervals. For instance, we are talking about, let's say, the interval from 1 to infinity, or the interval from negative to infinity to 3, stuff like that. So one or both endpoints, boundaries of the interval is infinity. The other one is the one that has a vertical asymptote or discontinuity within the interval. Okay? So this is the second type, f of x, or the integrand f of x has an infinite discontinuity. By that we mean a vertical asymptote. In the interval of integration. If you remember, earlier in the semester, I think, if not, we did it at the end of Calc 1, we looked at the integral of something like 1 over x squared dx. I don't know if you remember that. And we integrated from negative 2 to 1 or something like that. And we came up with the result, but we said, no, that's incorrect. Remember, again, let me say it again. You want to integrate from negative 2 to 1, the integral, you want to calculate the integral from negative 2 to 1, the integral of 1 over x squared dx. What's the problem over there? Right, exactly. You have to go through 0. You have to pass 0. You don't get $200 or something, but you have a vertical asymptote over there. So you have a point of discontinuity inside the interval. And we said that's why when we calculate like that, we came up with a value, but it was the incorrect value. And so this will be a type 2 improper integral. All right, let's look at type 1 first. Type 1, we are dealing with infinite intervals. And for an example, let's look at a function. So this is example. Let's say we want to integrate 1 over x squared, the same function that I talked to you about, from 1 to infinity. Okay? Now, in order to look at it, let's graph this thing, or sketch the graph. Okay. Well, we already know that this function has discontinuity at x equals 0, and it will go to infinity, so vertical asymptote over there. But it comes down from positive infinity and go like this, curves like so. And then when x goes to infinity, then 1 over infinity squared goes to 0. So here's the function y equals 1 over x squared, right? And now we know that when x equals 1, which is the left boundary, then y equals 1 as well, 1 over 1 squared. And now we go, and what we really want to integrate is the area between the graph of the y, the graph of the function, and the x-axis, like so. And we think, well, if this graph goes all the way to infinity on the right side, can we calculate the area even though the graph goes to infinity? Well, the answer is yes, we can. Not all the time, but in this case, for this particular function, we can. To do so, we'll consider first, let's calculate the area from 1 to t, some intermittent value t inside the boundaries. So between 1 and infinity, the boundaries of the integration, we pick up a value x equal t, and we calculate the area. And we call this, we're going to say that the area a of t, right, will be the integral from 1 to t of 1 over x squared dx. Now this we can calculate, right? So a of t is the integral from 1 to t of 1 over x squared dx. And let's see, what was the antiderivative of 1 over x squared? I believe it was negative 1 over x, right? And then we evaluated from 1 to t. So we have negative 1 over t minus negative 1 over 1, right? Yeah. So we have 1 minus 1 over t. Okay? So as long as t is a finite number, 100, 1,000, whatever, we can calculate the area. But of course I'm looking at this and I say, what happened when t goes to infinity? Then let's do the limit. The limit as t goes to infinity of a of t, or the limit as t goes to infinity of the integral from 1 to t of 1 over x squared dx is really the limit. I'm kind of writing the obvious stuff, but the limit of 1 minus 1 over t, and this will be simply 1. Agree? I'm so glad that you agree. So we can conclude that the integral from 1 to infinity of 1 over x squared dx can be written now as this one right there. It will be the limit as t goes to infinity of the integral from 1 to t of 1 over x squared dx. Okay, we got the 5-minute warning. So, and this will be, this will end up equal 1, and we have a value. Turn out that if we continue and shade all the way to infinity, then the area captured between the graph, between under the curve, going from 1 to infinity and above the x-axis equals 1. All right, let me give you, in the last 5 minutes, let me write a couple of definitions here, and we'll finish this discussion. So the definitions, let's do the first definition. Okay, we're going to say that if we have an integral from a to t of f of x dx, if this integral exists for positive values of for t greater than a, actually, for all the values of t greater than a, then the integral from a to infinity, in this case, of f of x dx will be the limit as t goes to infinity of the integral from a to t of f of x dx. And this is exactly what we did right here on top, except a was 1. Other than that, everything was exactly the same. And we have a provision here. And you can guess what is the provision. We know that some limit exists and some limit don't exist. So the provision is provided that the limit exists. It's not only exists, the limit is a finite number, because we can say, well, the limit exists, but it goes to infinity, right? That won't do us any good here. So provided that the limit exists as a finite number. So this should be 1. We have also another definition similar to that. If we go to negative infinity, and this would be written in the following manner. Bless you. We're going to say that if the integral from, let's say, t to b, another value, but you see that now the variable of integration is at the bottom. Here we have a to t, here we go t to b. So we are looking at the opposite direction, on the negative direction. So the integral from t to b of f of x dx exists, and in this case we are looking for values of x less than, for values of t less than or equal b. So the placement of t, as you can see in this graph, will be on the left side of the fixed value, in this case 1. Okay? Here we go forward, but in case 2 we go backward. Then we can say the following. We can say that the integral from negative infinity to b of f of x dx going to be equal to the limit as t goes to negative infinity of the integral from t to b of f of x dx. So in both cases we calculate the integral having this virtual or intermittent variable t as one of the boundaries, whether it will be the top boundary or the bottom boundary, and then we let the limit go to infinity or negative infinity. We let the limit go to infinity if t is the top boundary. We let the limit go to negative infinity if t is at the bottom boundary. Okay? Now, again, here we have the provision. So let me write 2 more sentences. Again, provided that the limit exists as a finite number. In other words, the limit equals finite numbers. We have also, in terms of terminology, we are talking about convergent and divergent improper integrals. We're going to say that the following, the improper integrals, and with that I'll finish, the improper integrals, both type 1 and type 2, or I'm sorry, case 1 and case 2, the improper integral, let's say from a to infinity of f of x dx, and negative infinity to b of f of x dx are convergent. Important word. We're going to run across this word quite a bit. If the limit exists, let's say the corresponding limit and are called divergent if the corresponding limit does not Okay, guys, I think this is the proper time to stop. I'll give you some more information tomorrow.